Hey everyone, welcome to this explainer from the Foundry by Forge College. Now, in our last lesson, we mastered measuring throughput improvements in Bitcoin. But today we're taking off the training wheels. We're going to see what happens when multiple Bitcoin scaling solutions actually collide. We've looked at these upgrades in isolated, totally controlled environments before. But today, we're heading out into the wild to watch these mechanisms interact and produce some truly massive, emergent scaling outcomes. It's honestly one of the most fascinating aspects of Bitcoin fundamentals, so let's jump right into it.
Okay, let's start with a little brain teaser. Because, well, when it comes to Bitcoin protocol upgrades, the math is delightfully weirder than simple addition. Think about clipping coupons at the grocery store. If you have a 20% off coupon and a 10% off coupon, you usually just add up the savings, right? You save 30%. But in the world of Bitcoin data weight, do a 21% reduction and a 40% reduction perfectly equal a 61% reduction? Hold on to your hats, because we're about to find out that sometimes in protocol engineering, 1 + 1 equals something way more exciting.
So here is our blueprint for today. We'll look at the transaction highway, modifying those lanes, the math of synergy, linear versus nonlinear synergy, and finally, your capstone game plan.
Starting with Section 1, the transaction highway. This is essentially our mental model for Bitcoin data. To really grasp this complex math, it helps to visualize the transaction lifecycle as a two-stage highway passing through a compression pipeline. Because, let's be real, reading raw hex code isn't fun for anyone, but we all intuitively understand traffic congestion.
Think of the witness lane as a special carpool lane, but one that is dedicated exclusively to heavy cryptographic signatures. Cryptography naturally takes up a ton of space. It requires all these complex mathematical proofs to ensure network security. So think of it as the bulky, multi-passenger van of the Bitcoin transaction. Before SegWit, these bulky vans clogged up the entire main road, fiercely competing for block space. But now they have their own dedicated, heavily discounted lane. Meanwhile, the base lane is your standard everyday traffic lane. This carries the essential, non-witness data. Basically, the fundamental who is sending what to whom information. These are your standard commuter cars. They're smaller, absolutely vital to the network economy, and they make up the core, undiscounted flow of our highway traffic.
Which brings us to Section 2, modifying the lanes, or traffic engineering the protocol.
Now that we've mapped out our highway, let's look at how protocol upgrades act like traffic engineers. We aren't just passively watching cars go by here. We are actively restructuring how they flow. When you map these upgrade mechanisms to their specific structural targets, the engineering is actually remarkably elegant. SegWit essentially clears out the base lane. Transaction batching? That packs more commuters into fewer cars, drastically reducing per-transaction overhead by sharing common data. Then you have Schnorr signature aggregation, which actually shrinks the physical size of those cryptographic vans in the witness lane by rolling multiple signatures into one. And finally, mempool policy acts as the traffic controller, determining speed limits and overall flow composition. This kind of structural mapping is the absolute secret to mastering network architecture and predicting throughput.
All right, Section 3, the math of synergy. This is exactly where 1 + 1 equals 3. Let's actually put this to the test and answer that brain teaser from earlier.
Okay, we start with a heavy, congested legacy transaction sitting at a hefty 1,008 weight units. Everything is just crammed into a single lane, paying full price. But simply by activating SegWit and moving those bulky signatures over to the discounted witness lane, we immediately drop down to 792 units. That is an isolated 21.4% reduction right out of the gate. A great start for sure, but just wait, it gets so much better.
Let's see how these upgrades actually build on each other. Throwing transaction batching into the mix drops us all the way down to 392 units. Now remember, by itself, batching was roughly a 40% reduction, and SegWit was about 21%. But together, they don't just lazily add up to 61%. Because they share a base overhead, they synergize to drop the total weight to 392 units, which is a massive 61.1% combined reduction. And for the grand finale, adding Schnorr's signature aggregation on top of Taproot shrinks that per-payment weight down to an astonishing 133.3 units.
So the absolutely crucial takeaway here is this. By attacking complementary parts of the weight formula, these combined upgrades yield a staggering 86.8% reduction, literally from 108 units down to just over 133. Because these upgrades optimize totally different parts of the transaction, some are clearing the base lane, others are shrinking the witness lane, their benefits actively multiply each other.
This is the true power of synergistic effects, and exactly why upgrading the network has such a profound impact on global throughput.
Moving to Section 4, linear versus nonlinear synergy, basically knowing how to count. That incredible drop we just saw proves that these effects multiply rather than add, but you really have to know when to expect which outcome. If you use the wrong mathematical model, your capacity predictions are going to be completely off base. Let's break it down. Linear additivity works when two tweaks shave bytes off the exact same fixed header. It's like if you and your friend both push a stalled car, your force adds up linearly. It's helpful, but incremental. But nonlinear synergy, that explodes when upgrades touch completely different accounting terms. It's like putting a vastly lighter engine in that car and then optimizing the aerodynamics of the chassis. You're altering entirely complementary resources, and suddenly the efficiency gains just multiply.
Knowing when to apply each model is key here. You want to stick to linear math for minor tweaks to the same resource, but switch to nonlinear math when dealing with complementary lanes or, and this is super important, when mempool congestion changes user behavior. Pay special attention to that last one. When the system is under heavy congestion, human behavior shifts, network fees spike, and users adapt their transaction types in real time. That behavioral feedback loop means you absolutely must use nonlinear reasoning to accurately predict how much traffic the network can handle.
And that leads us nicely into Section 5, your capstone game plan, preparing for measurement. Let's bridge the gap between abstract theory and real-world data.
So, knowing the theory is only half the battle, right? Measuring it out in the wild is where the real fun begins. For your capstone, you have to track specific metrics, things like witness byte fractions and average signatures per multi-sig setup. Why? Because joint distributions determine the combined real-world result. Simple marginal statistics just won't cut it here. You can't just look at average block size in a vacuum. You need to see how transaction batching prevalence interacts with SegWit adoption simultaneously. When we talk about joint distributions, we just mean looking for those overlapping areas where the data intersects and affects itself.
And hey, whatever you do not forget the human element. Treat human behavior and network policies as a core part of the system itself, because fee dynamics will absolutely alter your expected throughput. Technical savings don't happen in a vacuum. Think about it. If transactions get cheaper because of a cool new upgrade, people might just make way more of them. That entirely changes your mempool flow composition and eats right into that newly freed space. Economics and code, they are two sides of the exact same coin, and you have to weigh both.
So as you prep your capstone, keep this question in the back of your mind. What joint measurements will you need to capture the network's next emergent scaling breakthrough? As protocols evolve, the next massive leap in capacity isn't going to come from a single isolated fix. It's going to come from the elegant, nonlinear synergy of multiple upgrades all working together. Think deeply about what complementary resources are just waiting to be optimized next. To continue mastering these Web3 fundamentals and dive even deeper into this analysis, be sure to check out forgecollege.college. Thanks for hanging out with us, and we'll see you in the next explainer.